In the previous video, we reviewed Extrema from single variable calculus, and now we're just going to extend this idea to multiple variables. So we're going to still talk about mins and maxes, just as a point of order here, I guess. We are going to kind of restrict our focus to those functions that have n-dimensional inputs and single-dimension outputs. Okay, so just that definition is sort of pervasive here. So the first thing, we're going to talk about local min at a point existing if, and you might not find this so surprising, but just that if f of vector A is less than or equal to f of vector x, okay, for any vector x near vector A. Okay, and there's this language of near again. How do we think of that? Okay, we'll talk about that in a moment. Let's get our definition for the other one down first. And so maximum, you might say, well, Professor Bright, this isn't too surprising, but f of vector A is bigger than or equal to f of vector x. And again, that language of for any vector x near vector A. Okay, so what does this idea of near mean? That's kind of my first question that I want to discuss. Okay, and so what I want us to do is imagine an arbitrary set x. Okay, nice big blob. That's our general space or set x. Okay, and then here's our vector A. Okay, in set x. Okay, so what we want to do is look at this little teeny tiny region around A. Okay, and I'm maybe exaggerating the size of it a little bit here, but that's the sort of definition that I want to use here, is say, okay, well, I want to look at A and just a small region in formal mathematics, we think of it as a neighborhood, a small region near A. Okay, so the idea here is when we use near at this level of mathematics, what we actually mean is that there exists an R, and this is going to look similar to what we said before, such that if we talk about domain D as a set of all points such that the distance between x and A is less than R, that's the set of points. Okay, so we're saying that if vector x is in this domain D, then that's when we're going to say that forces f of vector x to be, and then something, either less than or greater than, whatever, greater than, f of vector A. Okay, so we're saying that that is a necessary condition for us to say that we have this minimum or maximum idea occurring. Okay, and also note that we are in our definitions of local max and min, we're actually allowing for equality. If we had just less than or greater than, and actually I should include that up here in these. If we had just less than or greater than, we talk about strict local extrema, so that additional adjective gets included when we do not have equality. Okay, just in case you run across that language. Okay, and then now let's just kind of talk about some examples. So if we're given a function, and yes, you might already have identified that this is a paraboloid. Okay, we like our paraboloids. They're nice examples. Okay, so if I draw this in three-dimensional space. Okay, and I have my x-axis, my y-axis, and my z-axis, and this is saying it's a paraboloid shifted 2 units along the x-axis, and so from there it hits the xy plane at 2, 0, and then from there it opens up. And you know I'm an awesome artist, so just bear with me, but it should look something rough. Nope. We're going to do that again. Undo. It should look something like that. Okay, and then we can do something like that in between. Okay, so paraboloid shifted up or over 2 units along the x-axis. So then, well, the question is, okay, what are our local extreme values? Well, we certainly know that there's a min of 0 at 2, 0. Okay, and so that's another way of, we can also represent this in a different way. We can say that f of 2, 0 is equal to 0, right? We know that. Okay, and then we also can say, well, we know it's going to be a minimum because for all x not equal to 2, 0, f of xy is greater than 0. Okay, and that last condition is actually going to allow us to say, yes, this is indeed going to be a local min. Okay, in our next example, okay, this one's a little more interesting because I don't know if we can create a picture, right? I don't think we can create a picture, right? We'd have to draw in 4 dimensions. Have fun with that. Okay? But then my question becomes, well, okay, in the absence of a graph, what can we do? And my answer is to look at it analytically, right? So this is positive, right? 1 is positive, and then this is always or this entire thing is always a negative number, right? If I include the negatives or the subtraction. Okay, so then this is going to mean that I'm going to have a maximum at, or maximum of 1, I should say. Prepositions matter. Okay, maximum of 1 at, and then the maximum is going to occur precisely when all those are 0. Okay, so and then I can also include the language that, okay, well, for all x not equal to 0, that implies that f of vector x is going to be less than 0. Okay, hence giving more weight to my argument of maximums and minimums. Okay, and I can actually go back and I could actually include the language of absolute. Okay, if you're unfamiliar or that language doesn't ring a bell right now, might want to go back to Calc 1 and check in Chapter 4 or so, maybe Chapter 5. Okay, and then so just some final remarks here. These are actually just local, these are absolute extreme values, right? That's what we ended up finding. So absolute extrema. Okay. Then my question is, well, how do we find it in general? Well, what we would do in single variable calculus, right? We would start by finding critical points, right? And then so we then have to do some things after that, but we're just going to do the same thing in multivariable. So we're going to talk about critical points in multivariable calculus as being when the derivative matrix is 0, or again, in our case, we can actually talk about the gradient just being 0 or undefined. Okay, so derivative matrix, gradient 0 or undefined. Okay, and so intuitively, critical points occur when the tangent plane, let me get my pen going, is horizontal. Okay, and this, okay, so this tangent plane works in the case of 2 and in the case of 3 dimensions, but much beyond that we have to use the language of hyper horizontal. So just some language clarification is we might have to talk about hyper horizontal, and that is just if we're in higher dimensions. Okay. Um, and then, so ideally what we do is we find these critical points and then we remember there's some more things that we have to do after that. Stay tuned to figure out what we do next.